So we are going to discuss about the force on a conductor kept in a magnetic field. Suppose this is a magnetic field and in this magnetic field a conductor is kept. Now the crosses represent that the direction of magnetic field is into the plane of the board or into the plane of the paper, towards the plane, not towards the reader, right? 90 degree inside, right? Now ये जो कंडक्टर है, ये कंडक्टर ये ऐसे भी हो सकता है, it could be at some angle and it could be like this and it could be like this. In the direction of the field, it could be at 90 degree, it could be held at some angle. So this is a conductor in which a lot of electrons are flowing. हमने अभी तक क्या पढ़ा है? That force on a charge. Whenever a charge is moving in a magnetic field, a moving charge will experience a force which is given by QVB sin theta, right? So conductor है तो it has a lot of electrons and every electron will have some charge. Every electron has a charge of 1.6 into 10 to the power minus 19 coulomb. So we know that force on every electron will be QVB sin theta. As per the diagram, ये कंडक्टर ऐसे रखा है, इसका लेंथ L है और इसमें कितना करंट फ्लो कर रहा है? I करंट फ्लो कर रहा है. If theta is 90 degree, the angle between the motion of the charge, current is flowing in this direction, it means electrons are flowing in downward direction, right? Electron flow and current flow will be, conventional current flow will be opposite to each other. So the angle between them is 90 degree. So if theta is 90 degree, then force is given by QVB sin 90, that is 1, right? So force comes out to be QVB. Let us say we are talking about a very small length. इस small length dl में electron flow कर रहा है. We are talking about single charge, right? On a very small length, and that length we always assume as dl. So if I am taking a very small charge dq, which is equal to the charge of one electron, say for example, then the small force on that length will be df is dq into vb. This is the force on the dl length of the conductor, right? Now we can write velocity as dl by dt. Velocity of the charge in length L will be dl by dt. So velocity can be written as dl by dt into b. So we can also write it as dq by dt into dl into b. This is the force on dl length. And what is dq by dt? dq by dt is I. So we can write df is I dl into b. Is that clear? Now the force on total length, हमने बोला कंडक्टर का लेंथ कितना है? L length है, right? So for L length we have to integrate both the sides. So what will be F? F will be I, B comes outside and the integration of dl will be L. So what is the force? Force is given by I into L, dl का integration L into B. So what is the force experienced by this conductor? Force experienced by this conductor will be I into L into B. Again, this force depends on the orientation of the conductor. हमने ये magnetic field लिया, अभी conductor ऐसे रखा है, ऐसे रखा है, ऐसे रखा है. It depends on that. So again, what we will do? Force is a vector quantity, current is a scalar. तो इन दोनों के बीच में कैसा प्रोडक्ट होना चाहिए? L और B के बीच में it should be a vector product, that is cross product. So it depends on how the conductor is kept in a given magnetic field. So we can write F as I L cross B, right? The magnitude will be I L B sin theta. A cross B is given by AB sin theta. So L cross B will be given by L B sin theta. It can be written as I, magnitude of force can be written as I L B sin theta. For our convenience, for learning it in a better way, हम इसको rearrange करके लिख लेते हैं F is equal to BIL sin theta, Bill sin theta. That is how we remember. B is magnetic field, I is the current flowing through the conductor, and L is the length of the conductor. So that is how, when we are talking about a single charge, a charge carries a force which is given by QVB sin theta. But if a conductor which is having a lot of electron is carrying a charge, then the force experienced by the conductor will be BIL sin theta or Bill sin theta or I L cross B. This you have to remember, children. You cannot write it B cross L. L पहले आएगा, L cross B. Is that clear? So force on a conductor in a magnetic field is given by BIL sin theta or Bill sin theta. Directly we write that. Right? Now we'll discuss the special cases. We'll discuss the special cases for this. First case, if theta is 0 degree or 180 degree, मतलब अगर ये मैग्नेटिक फील्ड इनटू द प्लेन ऑफ पेपर है और ये कंडक्टर भी ऐसे रखा है इन द सेम डायरेक्शन ऑफ द मैग्नेटिक फील्ड या ऐसे रखा है, आई रिपीट, magnetic field is into the plane of the paper, conductor is also kept like this at 0 degree or like this at 180 degree. In that case it will not experience a force. BIL sin 0 or sin 180 comes out to be 0. It means conductor will not experience any force. Conductor will not experience any force. Second case, if theta is 90 degree, then what will be F? BIL sin 90. Sin 90 is 1. So what will be the maximum? Then in that case conductor will experience a maximum force. ये कोई कंडक्टर हमने मैग्नेटिक फील्ड में रखा है, मैग्नेटिक फील्ड ऐसे है, कंडक्टर का लेंथ, बिकॉज द एंगल इज बिटवीन लेंथ एंड द मैग्नेटिक फील्ड, कंडक्टर का लेंथ ऐसे है, मैग्नेटिक फील्ड 90 डिग्री पे, तो इस केस में कंडक्टर विल एक्सपीरियंस अ मैक्सिमम फोर्स विच इज गिवन बाय BIL. हाउ डू वी फाइंड द डायरेक्शन ऑफ द फोर्स? वी फाइंड द डायरेक्शन ऑफ द फोर्स बाय अप्लाइंग द सेम रूल, दैट इज फ्लेमिंग्स लेफ्ट हैंड रूल. फ्लेमिंग्स लेफ्ट हैंड रूल जब हमने QVB के लिए लगाया था तो हमने क्या बोला था? दिस इज फोर्स, दिस इज मैग्नेटिक फील्ड, दिस इज द मोशन ऑफ द चार्ज. मोशन ऑफ द चार्ज मीन्स वेलोसिटी एंड मोशन ऑफ द चार्ज विल क्रिएट द करंट. तो हम इसको क्या बोलेंगे? मिडिल फिंगर को करंट. सो इफ a conductor, the motion of the charge along the length, right? So if a conductor is kept in a magnetic field where this is the current flowing in the conductor, and then this represents the force experienced by the conductor, right? In that case it will experience this force. Suppose current upward है, magnetic field inside है, अभी देखो जरा, current upward, magnetic field into the plane of the paper, तो ये कैसे होगा? Force will be towards me, towards west side. That is how we find the direction in the expression of F is equals to BIL sin theta.